Welcome students to this lecture, and we will continue our study of Sturm-Liouville systems in this video. So if you remember, we were talking about this sort of problem, right? L of y. So here L of y, we are going to define it like this, right? P of y prime whole prime plus q of y. Okay, that's our L of y. That is how we are defining L of y. Clear? Now the thing is this, as we have already talked about, this is an operator. For now we can just assume it to be C infinity of I. Okay, so the domain is C infinity of I and the range is C infinity of I. What do I mean by this? See, what I mean by this is it is taking a smooth function. This is, we will call it an operator L, taking a smooth function and giving you back a smooth function. Yes, okay. Now the point is this: here we were assuming that this P, Q and S, all of these functions are smooth, right? And what we have seen is the theorem 1 in the last video. If you remember, we talked about it. So let's say you have two distinct eigenpair. What do I mean by this? That lambda k phi k and lambda L phi L. So basically this is your eigen value, right? And this is your eigen function. Okay, so lambda L phi L. Let's say you have two distinct pairs. So basically what do I mean? Lambda k and lambda L are not going to be same. Is it okay? So are distinct pair, distinct eigenpair. Okay, distinct eigenpair. So if you start with it, then you can say that what is the relation between phi k and phi L is that phi k and phi L are perpendicular to each other with respect to the weight S. Phi k and phi L are perpendicular. What I mean is orthonormal. Okay, so orthogonal, you can say, not an issue. Orthogonal, huh? Orthogonal with respect to the weight function S, S of x. Okay. So of course in I, which is AB. Okay. Now we are going to explore more such relation. So first of all, what do we have? Two distinct eigenvalues, lambda L. So here we are assuming lambda k not equals to lambda L. Of course, this assumption is there. So you have the eigen functions. What is the relation between them? They are orthogonal. Yes. Now theorem 2. What we are going to do is we are going to talk about a little bit about a identity. So we will call it a Lagrange identity. Lagrange identity. Okay. So what is a Lagrange identity? Let's just understand this. So first of all, we are going to assume that y and z is in D of L. D of L, what do I mean by this? D of L is here. Let me write it this way. This is the domain of L. Domain of L. Okay, and in our case the domain of L is C infinity, which is C infinity I. Okay, but we can always write it as D of L. See, it does not have to be C infinity, it can be C2 also. Yes, but for our case we are just assuming it is C infinity, so we can go with it. But generally speaking, you can write it like D of L. So if you have two functions y and z which is in D of L, then the following identity holds. Then the following identity holds. Identity holds. Okay. And what do I mean by this? Let's just understand this. It means that y, L of z. Okay. So basically L of y is this, right? Yes. So L of z is just y replaced with z. So y L of z minus z L of y. So this beautiful looking identity is true. What does it say? It says that it will give you P y z prime. Where is P coming from? P is this leading coefficient P, right? P y z prime minus z y prime. Okay, this term and the derivative of this whole thing. Yes. See, P, y, z, all of these are very smooth functions, right? So all of these, the derivative exists, so we do not have to worry about all that. Okay. So this is an identity essentially. What does the identity means? It means that a relation which holds for any function essentially in this sort of cases. Okay. And the proof is extremely simple. Of course, I want you to do it yourself. But just for the sake of it, I will just give you an idea of what exactly needs to be done. Nothing actually is there. It's just a simple calculation. But basically what the proof says is this. You see, YL of Z minus ZL of Y. What is that going to be? It is essentially you have Y P Z prime whole prime plus Q Y Z, right? If you remember. So basically I'm just multiplying. See, L of Z is essentially this replacing Y by Z. And then you are multiplying it by Y. So basically you have this. Again, you have this particular term minus Z P Y prime whole prime minus Q Y Z. Is it okay? I think you have got this. And now, of course, it is very easy to check. See, these two terms are getting cancelled out, right? And this term, y, this is the first term and the third term, you can actually check this thing. Yes, I'm not going to do this for you. I need you to check this. This is this minus z y prime, and the derivative of that. Okay, very, very easy to check. So please do this part. Check. See, essentially what will happen is there will be an term which is going to get cancelled out. So essentially you will have this identity. Very, very simple identity. It's called a Lagrange identity. We are going to use it in a lot of different ways or places. Okay, right. So that's your theorem 2. Very simple. Okay, let's look at theorem 3 now. Theorem 3. So what do you have? See, it says that the operator L, right? The Sturm-Liouville operator. The Sturm-Liouville operator. So this operator, as I have already explained to you, this is called the Sturm-Liouville operator. Okay, Liouville operator. Operator. What is it? This is the L. Okay. So L is self-adjoint. What do I mean by this? I will explain to you. Self-adjoint. You have to, you already know what self-adjoint matrices are, right? So similar sort of idea. See, L here is this. Yes. See, L. Okay. L is this, right? L of Y is P Y prime whole prime plus Q Y. Yes. So maybe I can remove this. Otherwise, you will get confused. Let me do it this way. Yeah. So that's your L of Y. L of Y. Yeah. So this operator L, which is from C infinity I to C infinity I, that is self-adjoint. What do I mean by this? What I mean is this. That is L of Y acting at Z. Okay, the inner product of it. Again, we already talked about inner product here, but this is a different sort of inner product. This is an inner product in L2. I will explain to you what I mean by this. This is nothing but the inner product of Y acting at L of Z. Okay, and this holds for all yz in D of L. In our case, D of L is C infinity. Okay, but it can be C2 also. It's not an issue. Okay, so in our case, this is the C infinity. Okay, now what is this inner product? And the inner product, let me define it. The inner product of f and g in this case, yes, this is a little different. This is defined as integral a to b f of x g of x dx. Okay, so initially the inner product, if you remember, we were talking about inner product while talking about the orthogonality, and then we defined it with respect to some weight. Here the weight is going to be 1 essentially. Yes, so that's basically your self-adjoint. It means that Ly acting at z is nothing but y acting at Lz. Is it okay? Right. Oh, one second. I'm sorry. This is f acting at g bar, f times g bar dx. So if g is real valued, so it is basically a to b f of x g of x bar dx. Is it okay? Okay. Proof. Let's look at it. Sorry. If it is real valued, there is no bar. So it is f times g. So now let's look at the proof. So first of all, you do have to check this. Yes, this is very simple thing to check, that L of z, okay, the bar of that, yes, is nothing but L of z bar. Yeah, this is true. Why? Because P, Q and S are real valued in our case. Real valued. Okay. So this particular thing is of course true. Yes. So please, you have to check it. This is just one line thing. Very, very simple to check. Okay. Now, if that is true, let's understand what happens. See, Ly acting at Z. Again, this is very, very simple. Okay. The inner product of it minus y acting at Lz. The inner product of those two. What is this going to be? This is nothing but a to b z bar L of y minus y L of z bar with respect to dx. Is it okay? Now, this, now if you remember this particular thing, you see from Abel's, from Lagrange identity, YLZ minus ZLY is P YZ bar minus ZY bar whole prime, right? So we are going to use that part here. So the integral and the derivative part is going to can be getting cancelled out, and the only thing which remains is this P of Z bar Y prime minus Y Z bar prime evaluated at the point A to B. I hope this is clear. Okay, this is what we are going to left out with. Why? Because there is this derivative. You see, this derivative part is there. This derivative. So the integral and the derivative is getting cancelled out. So it becomes just this function evaluated at the point A to B. Okay. Now you see, since this the operator P, this is our initial assumption. If you remember, we assume that this P, yeah, see, P is generally positive. Yeah, we can, without any loss of generality, we can assume it. Okay, so P is generally positive. Okay, so let's say that since P of A is positive, then A1, see, it satisfies the regular Sturm-Liouville boundary condition, right? So these two condition, this two condition is satisfied, right? So since this two condition is satisfied, what do we have? Y and Z will satisfy that condition. So we have A1 times Y of A plus A2 times Y prime of A is going to be 0. And similarly, A1 times Z bar of A, okay, I think I should write it like, yes, mine plus A2 times, 1 second, yes, Z bar prime of A, this is going to be 0. That's just a boundary condition. See, Y and Z bar, for Y and Z bar, we are just writing it like this. That's the only thing, okay, right? Now, the thing is this, see, these two equation, yes, these two equation, this is the set of equation, right, system of equation, and we have this condition A1 square plus A2 square is non-zero, right? So that will give me that the coefficient matrix, whatever it is coming, yes, that is going to be 0, right? So therefore Z bar acting at A, Y prime acting at A, minus Y acting at A, Z bar prime acting at A is going to be 0. Yes, see, since this system has a non-trivial solution, so the coefficient matrix has to be 0, right? So, coefficient matrix has to be singular, right? That's just your system of equation, this thing, linear system of equation theory, right? Okay. Now, so this is true. Now, if this is true, this actually implies that L is self-adjoint. Yeah, if you see, this is what we need. If this is 0, then this particular thing, if you look at this particular thing, this actually is, if you write it like this, see, this is P of B, Z bar acting at B, Y prime acting at B, minus Y acting at B, Z bar prime acting at B. Is it okay? Yeah. So this minus, again, P of A, same thing with replaced by A. Z bar acting at A, Y prime acting at A, minus Y acting at A, Z bar prime acting at A. Is it okay? Now you see, this particular thing is 0. So this whole thing is going to be 0. And similarly, since I did it for A, but the same thing also works for B also. So this is also going to be 0. So again, that will give me that this whole thing is 0, and L is a self-adjoint operator. I hope this is very, very clear now. Okay. So what did we learn? Let's just recall once that for this operator L of y is P y prime plus Q y, P Q, P is positive, and we are assuming that L is a function operator from L infinity to L infinity. First of all, we have looked at this Lagrange identity, that this sort of identity holds, and with the help of Lagrange identity, we showed that the Sturm-Liouville operator is going to be self-adjoint. Is it okay? Now, what we are going to do is use this self-adjointness to show a very, very important property. So, this is theorem, once again, theorem 4. What do we know about theorem 4? From theorem 4, what we can say is this. All the eigenvalues of I will write it like this, regular Sturm-Liouville boundary value problem. Yes, of course, with Sx positive. This is our initial assumption also, okay? So, I do not have to write it, but still is real. If you remember, in the first lecture of Sturm-Liouville problems, we worked out a exercise, right? And in that exercise, we were talking about when is there a eigenvalue. But we checked that for positive eigenvalue, negative eigenvalue, and zero eigenvalue. But we did not check for a complex eigenvalue. This is the reason. Because all you need to see is if the system is a regular Sturm-Liouville boundary value problem or not. If it is, then you can say that all the eigenvalues are going to be real. Okay. So let's look at the proof of this thing. The proof is very, very simple again, using the theorem 3. Okay, that it is going to be self-adjoint. So let's say that lambda and y, okay, and this is an eigenpair. Is any eigenpair? I don't care, some eigenpair is any eigenpair. Okay, let's start with that. Yes, and what do I mean by this? That is L of y plus lambda sy is going to be 0. Of course, y is non-zero. Why non-zero? Because this is an eigenfunction, remember? So then, if this is the case, you see, L is a self-adjoint operator. So, for any yz, this particular thing is true. You see, Ly acting at z is y acting at Lz. So, this is always true, right? So, I can replace z with L and still the same equation holds, okay, the same thing. So, essentially replacing that, it becomes 0 equals to Ly acting at y minus, once again, let me put it this way, otherwise you may get confused. Ly acting at y minus y acting at Ly. Okay, see, here in this thing, it is self-adjoint, right? So for any yz in the domain of L, this identity, this particular thing is true, that Ly acting at z is y acting at Lz. So I am just replacing z with y here, and so that will give me that this particular thing minus this particular thing is going to be 0, right? See, and then that will actually imply that lambda minus lambda bar, okay, a to b s of x yx square dx. This actually will give me this particular property, right? See, let's say that lambda y is an eigenpair. If there are complex eigenvalue, okay, if lambda is complex, then lambda bar is also going to be there, right? Okay, so if that is the case, then this thing is true even if you replace lambda with lambda bar. Is it okay? Yes. Okay, so we will replace that and we'll put it together. So basically, in this case, Ly acting at y minus y acting at Ly will look like this. Okay. Now you see, S is given to be positive. Since S is given to be positive and y is non-zero, Okay, that will imply that this particular thing has to be equals to 0. So that will imply lambda has to be equals to lambda bar. That will imply that eigenvalue lambda is real. I hope this is clear. Okay, if it is not clear, again let me explain again what we are doing. Let's say that we start with an eigenpair lambda y. Is it okay? And for all, I mean, purposes, what we are going to do is this. If Ly is an eigenpair, this thing is true. L of y plus lambda Sy equals to 0. Is it okay? Now, the thing is this. You see, also, if lambda is going to be, so you see, initially we are not assuming that lambda is real or not. It can be any, I mean, lambda is in C essentially. Yeah? Here, where we are assuming lambda is in C. So in this case, Ly plus lambda Sy is going to be 0. Yeah? And similarly, we can also say that L of y. So if lambda in C satisfies this equation, lambda bar will satisfy L of y plus lambda S of y bar. This particular thing, if you do, that is going to be 0 also. So this will give you L of y bar plus lambda bar Sy bar is going to be 0. This is what you are going to get, right? If you understand it properly, taking the complex conjugate, that is. Yeah. Now, if you do that, then of course you can check that. Oh, one second. I made a small mistake here. I should write it as L of y bar minus y bar L of y. Yeah, I hope this is correct now. Yeah, this is fine. Yes, now it is okay. Fine. So once I do this, now you see, if you multiply this thing by y bar and multiply this thing with y, then you see y bar L of y plus lambda s y bar, which is mod y square. This is going to be 0. And again, y L of y bar plus lambda bar s of mod y square is going to be 0. Now you just take the difference, it is going to be this. And since s is positive and y non-zero, lambda has to be equals to lambda bar. I hope this is clear now. Okay, fine. Maybe I will leave it here, yeah, for your understanding. Let us just leave it here. Okay. So what did we learn? That the regular Sturm-Liouville boundary value problems, if you are looking at just the eigenvalues, they are going to be real. Is it okay? Maybe I can do it in the next. Okay, maybe I will do it here. The next theorem, sorry, is this. So let's say that phi1 and phi2, two eigen functions, are any two solutions of Ly plus lambda Sy equals to 0. Okay, in I, any two solutions. So maybe I can put it this way. This is different. Clear? Okay. Then what we can say is this. What is the relation between phi1 and phi2? P of x. Okay, the P of x is the leading coefficient, if you remember. The Wronskian at the point x of phi1 and phi2. This is always going to be a constant. Okay, this is a very, very important property. This, what do I mean? This is, what do I mean by this? This is basically the Wronskian of phi1 and phi2 at the point x. Is it okay? Yes. And if you remember, what is Wronskian of phi1 and phi2 at the point x? The definition is this. It is phi1 phi2 prime minus phi2 phi1 prime acting at the point x. That's its definition. Okay. So what we know is this. Let's say if you fix a lambda, yeah, and you have two solutions. We do not care what is the relation between phi1 and phi2. Any two solutions, phi1 and phi2, corresponding to lambda. So think of it like this: lambda phi1 and lambda phi2 is basically eigenpairs. Okay, we don't care about what is phi1 and phi2 in this case, any two phi1 phi2. What we can say is this, that the Wronskian p, of course p part is there, p of x times the Wronskian of phi1 phi2 at the point x is going to be constant, and this holds for all x in AB. Yeah, I hope this is clear. Now let's look at the proof of this thing. Again, this is very simple proof. Yeah, proof. See, if this is true, then p phi1 prime plus q plus lambda s1 acting at phi1 is going to be 0. And similarly, p phi2 prime plus q plus lambda s, maybe I can write it as, sorry, yeah, there is a simple mistake here. S acting at phi2, this is going to be 0. So this is times phi2, this is times phi1 I will do. Okay. So both this relation, the first relation I will multiply it by phi2, the second relation I will multiply it by phi1. So if I do that, you see what I am going to get is this, phi1 p phi2 prime minus phi2 p phi1 prime. This is going to be, sorry, yeah, by mistake I put it here. This is going to be 0. Is it okay? See, this q plus lambda s phi1 phi2 is getting cancelled out. So essentially we are only left out with this. And we have already known that this particular thing, we can write it like this, p times phi1 phi2 prime minus phi2 phi1 prime, okay, acting at the point x is 0. So this holds, sorry, one second, let me do it this way. So this particular relation, if you remember, we can write it like this, right? P phi1 phi2 prime minus phi2 phi1 prime, okay, the derivative of it is going to be 0. Okay. Now if this is true, then we can integrate it between a to b. So maybe I can write it again, so it becomes more clear here. This particular relation, when integrating between x and a, between x and a gives p of x phi1 of x phi2 prime at the point x minus phi2 at the point x phi1 prime at the point x. This is equals to p at the point a phi1 at the point a phi2 prime at the point a minus phi2 at the point a phi1 prime at the point a. This is what we are going to get. Now see that this particular thing, phi1 at the point a phi2 prime at the point a minus phi2 at the point a phi1 prime at the point a, this one second, yes, okay. So this is nothing, you see, this particular thing, this term depends only at, of course it depends on phi1 phi2, but all of that is fixed and p is fixed. So this particular term depends only on a. So depends only on a. Okay. So this is basically nothing but a constant. Okay. And so if this is constant, it means that this particular relation is constant, which is independent of x. So basically it means that p of x, and if you understand, this is nothing but, it is the Wronskian of phi1 phi2 at the point x. Phi1 phi2, this is nothing but constant. Okay. So px times the Wronskian at the of phi1 phi2 at the point x is definitely going to be constant, and this particular thing, relation, is called the Abel's formula. Abel's formula. I hope this is clear. And see, this relation does not depend on x, so this holds for all x. Yeah, so this holds for all x in AB. Okay, right. So with this we come to the last theorem of this particular lecture, which is theorem 6. I hope this is theorem 6. Theorem 6. Okay. So what it says is very, very simple. It says that an eigenfunction of a regular Sturm-Liouville boundary value problem, okay, is unique except for a constant factor. Okay, factor. So what do I mean? I mean that if you have eigenfunction lambda and okay, maybe I can write it here. That is if lambda phi1, okay, and lambda phi2. So basically one lambda is there, and corresponding to that one lambda you have phi1 and phi2, okay, two different eigenfunctions, okay, are any pair of eigenfunctions. If this is the case, then what we can say is phi1 is equals to c times phi2. That is, they are linearly dependent. Yes, I hope this is clear. So basically what I am saying is this. See, if you remember the first theorem, what it is saying is this: two distinct eigenfunctions and the eigenvalues two distinct eigenvalues and the eigenfunctions corresponding to them are orthogonal with respect to the weight function. This theorem says that the eigenfunction, the eigenvalue is essentially same, lambda, but you have two different eigenfunctions corresponding to the same eigenvalue. If that happens, then those eigenfunctions are nothing but linearly dependent. Okay, so a little different. So how do you prove something like this? Let's look at the proof of it. So let's say that lambda and phi I be any pair of eigenpair, okay, for I equals to 1 and 2. So basically for I equals to 1, this is an eigenpair, and then I equals to 2 also there is an eigenpair. Okay. Now you see, by the previous, you remember Abel's formula, we just looked at it. Abel's formula, what does it say? It says, you see, the Wronskian thing. Yes, px times the Wronskian. See, this is also a lambda is same. You see, lambda is same. Okay. So from Abel's formula, what do we have is px times the Wronskian of phi1 phi2 acting at the point x is going to be constant. Okay. Now you see, if this is the case, now let's look at it. See, phi1, since phi1 and phi2 are two solutions, right? Phi1 and phi2 are two solutions. So basically they will satisfy the of 1 plus 2. Okay. So phi1 and phi2 will satisfy the boundary condition. So that will give me a1 times phi at the point A plus a2 times phi1 prime at the point A. This is going to be 0. And similarly, a1 times phi2 at the point A plus a2 times phi2 prime at the point A. This is going to be 0. Yes. Now again, since both a1 and a2 cannot be simultaneously 0, together they can't be 0. So what does that give me? That the coefficient matrix is going to be 0, right? So it means that the Wronskian of phi1 phi2 at the point A, is definitely going to be 0. This system has a non-trivial solution, implies that the coefficient matrix has to be singular. Yes. Okay. Now if the Wronskian at the point some point A is 0, it means that will imply that the Wronskian at every point is going to be 0 of phi1 phi2 is going to be 0. Yes. Why is it true? By Abel's formula. You see, Abel's formula says that this is constant for all x in AB. Clear? Now, at the point A, if this is 0, then at any point, this is going to be 0. Yeah. So, if at the point A is 0, it means that for any point it is going to be 0 since P is always positive. Yeah. Since P is always positive. Is it okay? So, if the Wronskian is 0, we know from our ODE theory that therefore that will imply that phi1 and phi2 are linearly dependent. Okay, what do I mean by this? I mean that is phi1 equals to c times phi2. Is it okay? For some constant c. So essentially, for same eigenvalue lambda, two distinct eigenfunctions phi1 and phi2, they has to be they differ only by a constant for some constant c. Is it okay? So with this, I am going to end this video. In the next video, we are going to explore more about regular Sturm-Liouville boundary value problem.